we should hopefully be able to intuitively guess that a differential equation is just an equation that has a derivative in it, right? And the order of that differential equation is just the order of the highest derivative involved. So this differential equation, dy dx equals secant squared x plus 2x plus 5, is just a first order differential equation because the highest derivative in it is a first derivative. But sometimes we might have a second derivative or a third derivative. If the highest derivative is 3, then it's a third order differential equation. And so on and so on. There's entire classes on differential equations. What we're going to do over the next day and a half here just sort of scratches the surface on what differential equations are all about. So when you solve a differential equation, all you're really being asked to do is find all the functions that satisfy that differential equation. Just like when you're asked to solve an equation, you find all the x values or whatever variable you're looking for, you find all those values that make it true. Well, you do the same for a differential equation. You find all the functions that make this derivative or combination of first and second and third derivatives or makes a fifth derivative true. And so all we have to do to solve them and to find a general solution with no initial conditions given is to integrate. So effectively what we do is we take this dx, bring it over here, and then integrate both sides. So our integral of dy is just an integral of 1 dy or y, and integral of secant squared x plus 2x plus 5 dx should just be tangent x plus x squared plus 5x plus. And since, like I said, there's no initial condition given to us that we have to have x equals 7 and y equals 3, we can't find an actual value for the constant. So this represents the family of functions that solves this differential equation. We call this the general solution to the differential equation. Nothing different than any basic regular integration. Just integrate, put your plus c, call it good. Easy enough.
Totally.
What's that?
Totally.
Totally, yes. Okay, so then we will now start to introduce some initial conditions. So if we have an initial condition, like the solution to our differential equation has to have its graph pass to the point 1, 0, well, we call that an initial value problem. And it's still, still a differential equation that has an initial value. And it has one particular solution. It has a unique solution, at least for our purposes. There's only one function that has this as its derivative that will go through the point 1, 0. And so all we do is the same thing, bring that dx over, integrate both sides. Integral of dy is just y. Integral of e to the x is just e to the x. And the integral of minus 6x squared ought to be just minus 2x cubed plus our constant. And now we introduce our initial condition that when x is 1, y is 0. So we'll plug in 0 for y, 1 for x, and we'll end up finding our constant, which is, in this case, e, right, minus 2 plus, I don't know why I put a c over there, that's a 0, plus our constant. So our constant is 2 minus e. Let me just go back in and we write our function that satisfies this, e to the x minus 2x cubed plus 2 minus e. And if we take that function's derivative, it gives us e to the x minus 6x squared. And if we plug in 1 to it for x, we end up getting 0 for y. Easy enough?
Yes.
Wonderful. All right. Let's do another one. Nice, simple, easy one. We want to find the particular solution to dy dx equals sine x plus 2x that has a y-intercept of 3, which tells us an initial condition of when x is 0, y is 3. Bring our dx over and integrate. Y equals, our integral of sine ought to be negative cosine x. And our integral of 2x ought to be x squared plus our constant. We'll plug in 0 for x, and y will be 3. So negative cosine 0 ought to be negative 1 plus 0 plus c, giving us a constant of 4. And our function ends up being, that is the solution, the particular solution to this differential equation, y equals negative cosine x plus x squared plus 4. Good or no?
Indeed.
Great. All right. Maybe a last one or two of these here. Nice easy one again here. Bring over the dx and integrate. Gives us y equals x squared over 2 minus tangent x plus our constant. And our initial condition is that when y is 3, x is 0, giving us a constant of 3. And we end up with y equals x squared over 2 minus tangent x plus 3. And we have something different going on here than we did with any of the previous differential equations, or with the previous solutions to our differential equations. And what's that? What makes this function different from this function and this function? The two that had initial conditions that we already did. Those of you that were in my class last year should definitely know the difference between these functions and what we're leaving off here. But now I just feel all of the shame that you should feel about forgetting this. The difference is this function has tangent of x in it, and tangent of x has some discontinuities in it. It has some vertical asymptotes, in fact, right? It has some infinite discontinuities. And so whenever we solve a differential equation to find a particular solution, we can only guarantee that our solution is valid on the continuous portion of the domain of our function that includes our initial condition. So we have to think about this function and its discontinuities. So where does x squared over 2 minus tangent x plus 3 have discontinuities? At x equals, let's say, negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, and so on, right? Infinitely every pi at increments of pi over 2. Pi over 2, 3 pi over 2, pi over 2, 7 pi over 2, and all the negatives as well. True? Tangent of pi over 2 is undefined, right? Going up to a vertical asymptote there. Right. Yes or no? Yes. Okay. So what we have to do is we have to select the continuous portion that includes x equals 0. So between which two asymptotes does x equals 0 fall? This should be the easiest question that I've asked you all year. Between which of these numbers does x equal 0 fall?
Between negative pi over 2 and pi over 2.
Yeah, because one is negative and the other is positive. And so we're only guaranteed that this solution is valid on this interval. For any other interval, we might still have the same derivative, but we could have any other constant that we wanted to. And that won't affect this initial condition. But we have to have this specific function on this specific interval in order for it to be true. Any other interval, and put any constant you want in there, put plus 1,000,000 for all the rest of them, go for it, doesn't matter. As long as it's plus 3 between negative pi over 2 and pi over 2. We didn't have to worry about that here because this function is continuous for all real numbers. There are no discontinuities here, right? Same thing here, there's no discontinuities, right? Didn't have to worry about it here, even though there was discontinuities, because we weren't solving for a particular solution. This was just a general solution. So there wasn't one specific place we needed to pin down our function in between. But here, we had a particular solution with discontinuities, and so we have to pin down our solution on this interval. Good or no?
Yeah.
All right, so let's do another one like that. In fact, why don't you guys take a minute or two and work through this one on your own and see if you can get the correct interval on which the solution to this differential equation is valid. Ready, go. So take your dt, bring it over, integrate both sides. Integral of dA is just capital A. Integral of 1 over t is natural log absolute value t. Integral of negative 1 over t squared ought to just be what? Plus 1 over t, and then plus 6t, and then plus our constant. Everybody agree with that?
Yes.
All right, perfect. So plug in your a equals 0, plug in your t equals 1. And what'd you get as your constant? Negative 7. And we got a equals natural log absolute value t plus 1 over t plus 6t minus 7. And there is only one discontinuity in this. Where is that discontinuity?
When t equals 0.
Yeah, so t cannot be 0. And so we'll say this is valid for 0 to infinity. And if we wanted to, we could now eliminate the absolute value on that, because we're now only talking about positive numbers here, and the absolute value becomes redundant. But if you leave it on, that's also fine with me. Good or no?
Yes.
But everybody got that? No issues there? Cool. All right. We can apply this to basic motion problems to figure out the, let's say, the position of a particle, giving a velocity function, and some other information about the position. So if we want to find the position function, we just need to integrate the velocity function, right? So the integral should be a position is equal to the integral of this, which is 1/2 t to the 4th plus t cubed plus some constant. And we should be able to plug in 2 for t to get out 1 for x. So 1 equals 1/2 of 2 to the 4th minus 2 cubed plus c. And we'll have 1 equals, what does that become? 8. That was a plus. Sorry, I don't know why I've changed those to a minus. 8 plus another 8 plus c, giving us a constant of what? Negative 15. And so we would say that the position function should be equal to 1/2 t to the 4th plus t cubed minus 15. And then we can use that to evaluate our function at any point we want. So we can find x of 3 by just plugging in 3. And what does that come out to be? 81/2 plus 27 minus 15. So 81/2 plus 12, which is what, 105 halves? Good or no?
Yes.
Cool. All right. We'll just do this together.
Okay.
That should have been a v sine of t there. Messed up my variables. So a of t is sine of t. You can read that as a t now. That's a t. Perfect. So v of t ought to just be the integral of sine of t, which ought to just be negative cosine t plus some constant. And all we need to do is plug in 3 for v of t and negative cosine of pi plus our constant. And the cosine of pi is -1, so that becomes a +1. So we've got 2 as our constant. V of t is equal to negative cosine t plus 2. And then if we want v of pi over 3, it's negative cosine pi over 3 plus 2. Cosine of pi over 3 is what? Half. So that's -1/2 plus 2, or 3/2. Pretty straightforward. Everything should be I would hope really, really easy so far. I'll have you guys do this one on your own. So this one, we're going to go from an acceleration function to a position function to find the actual value of the position function at 2. So you're going to have to take 2 steps here. It's kind of like having a second order differential equation here with 2 little initial conditions, one for velocity to find its constant, and then one for position to find its constant. So I'll give you 2 or 3 minutes to do that, and then we will make sure you got it all correct. Everybody feel like they could do that one?
Yep.
Yeah.
Ready, go. So first off, v of t was what? T cubed plus 2 squared over 2 plus t plus our constant. And if we plug in 2, we should get 9. So 2 cubed is 8. 2 squared over 2 should just be 2 plus another 2 plus our c gives us what? Our constant is, looks like -3. And so v of t is t cubed plus t squared over 2 plus t minus 3. And our position function then should be t to the 4th over 4 plus t cubed over 6 plus t squared over 2 minus 3t plus our constant. And we should get 6 if we plug in 1. So a 4th plus a 6th plus a half minus 3 plus our constant gives us a constant of, let's see, 9 minus a half minus a 4th minus a 6th. What does that come out to be? What'd you get?
97/12.
97/12. You guys all agree with that? Let's see, what is that? 3, 5, and 11/12. Yeah. 9. Yep. All right, I agree with that. Okay. So c is 97/12. So our position function x of t should be 2 to the 4th over 4 plus t cubed over 6 plus t squared over 2 minus 3t plus 97/12. And we want x of 2. And it's not a huge deal to be, I'm sure you can all evaluate this, but 4 plus 4/3 plus, what's that, 2 minus 6 plus 97/12. 4, 2, negative 6 will cancel. That's nice. So this is just 16/12 plus 97/12, which ought to be 113/12. Good or no? That's what y'all got?
Yep.
Perfect. All right. Now, what happens if we can't actually integrate the function that we are given as a derivative? But we are still given an initial condition, because e to the negative x squared, I don't believe any of you are going to be able to integrate that. Would you agree? Yeah, I agree too. There is no function that has e to the negative x squared as its explicitly defined derivative, right? There is no function that is the integral of e to the negative x squared that is an explicitly defined function. So how can we find a function to represent this? Anybody have any thoughts?
Wait, first, how is this even like a situation if we're trying to find f of 7, but f of x doesn't exist?
It does.
Oh, there's just like no explicitly defined function for it, is
Correct.
what you're saying? Okay.
Exactly. Yes.
So then how is that function defined?
Well, that's a more difficult question to answer. It's got, there are functions there. Okay, what's the best way to say this? There are functions that there is a function, or there is a graph of something that when you take its derivative, it looks like this. It looks like e to the negative x squared. I think that's the best way to say it. Yeah. So there's a function whose derivative looks like e to the negative x squared, or there's a graph of something in the coordinate plane that looks like e to the negative x squared is the derivative. But there is no way to write a function that explicitly has this derivative. And so people have made up a function to call it's called the Gaussian error function, is what the integral of this e to the negative x squared function is technically called. But it's not, like I said, it's not a real explicitly defined function. And so there are times in higher math classes and whatnot where you might need to evaluate that function, or need to evaluate the integral of this e to the negative x squared at some value, given some point that you know that the original function needs to go through. And so that's sort of the situation that you might end up in. So I was going to add to this down here at the bottom, something like, let's find f of 2. Right? So suppose they asked us to find f of 2 if we were given this situation. And we should be able to use our calculator to find it. But the question is, how do we do that in a nice, simple, easy way? Does that answer your question or no?
Yeah.
Okay.
Could we like integrate by parts or something?
No, we don't need to integrate it at all.
What if we set it as a definite integral from 7 to 7? So then it's just 0, and you can solve for the constant.
Great idea. Let's say that f of x is equal to an integral of e to the negative, we'll just call it e to the negative t squared dt, plus some constant. And if we were to put an x up here and some other constant down here, I'm just going to write constant for now, but I'm going to replace that in a second. What's the derivative of this function that I just wrote? According to the fundamental theorem of calculus, it's just the original function evaluated at x, right? This constant goes away. This is just a constant, so that when I integrate and get a number and then take the derivative, it also goes away. So I want to put the constant of 7 down here, so that when I evaluate f of 7, I know what the integral from 7 to 7 of e to the negative t squared dt is. It's 0, which gives me a constant of what? If this integral is 0, this should give me the constant is 3. And so we end up with f of x is the integral from 7 to x of e to the negative t squared dt plus 3. And we can use that little trick to approximate the value of f of 2 using our calculator, because our calculator will just approximate this to a very, 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 very accurate value just by using one of our regular approximation methods. Right? You can use trapezoidal or rectangular approximation to evaluate this. So all we need to do is evaluate the integral from 7 to 2 of e to the negative t squared dt, and then add 3 to it on your calculator, and we should get a value. And you'll put in the t's as x's when you do it in your calculator. But does that make a little bit of sense on how to find this value? We like to ask a question like this in the calculator multiple choice section usually on the AP test. So good thing to know. Any issues there or no?
If they ask a question like this, well, actually, nah, never mind.
I mean, if they ask a question like this is literally exactly what you will do. If it's a function that you can't integrate. Or if it's on the calculator section, you could do it with any function if they give you an initial condition. I mean, their answer is in a decimal form. So
Are there ways, and I'm just curious, are there ways in like higher level math classes to tell the difference between like functions that like there's literally no explicitly defined integral of and functions that you might just be too dumb to figure out the integral of?
They're not exactly. I mean, no, there's not like a set way of knowing, oh, this one I can and this one I can't for functions that look like this. There's just, I mean, there's a set of, when I say set, I don't mean set in the, like, in the sense that there's like the math sense of like set theory. There's just like, there's a group of functions that are well established that people just know that you can't integrate. But
I see.
there are others beyond those too, but the most famous of them is this one, e to the negative x squared, because it's got this other thing called the Gaussian error function that's been written as its integral. But no, there's lots of other ones. So did anybody get a value here?
I just got 2.995 or 2.996.
Anybody agree with that?
Yep.
Yeah.
Cool. All right. Very good. Just as a point of note, I mean, like I said, there's lots of other ones, but a couple of the cool ones that you might think might not be that tough to find an integral of, but that you can't. There's ones called the sine integral, which is just sine x over x. You can't integrate that. Same with 1 over ln x, which is the logarithmic integral. And like I said, there's tons of other ones. There's what is the I can't remember what it is. It's the square root of 1 minus x to the 4th. I can't remember what that one's called, and it's a stupid basic name that I should be able to remember, but I don't off the top of my head. And like I said, there's a bunch of other ones. So, everybody feel like they could do this or no? Just to make sure, let's say that dy dx equals, what did I just use? E to the negative x squared, right? Yeah, so we'll say sine x over x, and let's say that f of 1 is equal to 2. We want to find f of 3. All right, so let's see if you can do this and approximate the value of f of 3. I'll give you guys just a minute or so there to write it out and see if you can do it. Ready, go. Cool. So hopefully you wrote this out as y was equal to the integral from, since we had 1 that we were going to plug in, 1 to x of sine of t over t dt, and then the constant that you'd end up with is 2. And so you just evaluated the integral from 1 to 3, sine x over x dx plus 2. Yeah? And what did you get when you did that?
$2.903.
903. Yeah, everybody agree with that?
Yep.
Cool. Easy enough. So sometimes they'll throw one of those on the calculator section of the multiple choice. So good to know how to do those. All right. Next thing we're going to talk about is sometimes we may have a differential equation that we may not be able to solve. And that's potentially because it might involve x's and y's that are not being multiplied or divided by each other, and we're going to deal with how to do the ones that are multiplied and divided. Probably not today, but we'll probably do that tomorrow. But sometimes it's necessary to sketch what we call a slope field to just approximate what the solution curve to a differential equation actually looks like. And so we're going to do a couple of quick slope fields. And the idea of the slope field just comes from the idea of linearization. Right? So a derivative, dy dx, is just the, it's just the derivative, it's just the slope of the tangent line to the function that is the solution to this differential equation. All right, so we know that the solution to dy dx equals cosine x is just y equals sine x plus any constant that we want. But if perhaps we didn't know what the actual solution to that differential equation was, it might be helpful for us to draw a bunch of little slopes at a bunch of different points in the plane that we could then sketch a curve through to give us a general idea of what the solution looked like. So we're going to do that with a nice easy one like cosine x right now. And all we have to do is pick x values because only x will affect the derivative here. Y values won't. So if we pick an x value of, let's say, 0, the slope of the line tangent to y should be 1 because the cosine of 0 is 1. And so anywhere where x is 0, we should have a slope of 1. We'll just draw a bunch of little slopes of 1. And suppose, and I should probably write that, cosine 0 is 1. Suppose we did cosine of pi over 2. Well, that would be what?
All slopes of 0.
Yeah, that should be 0. So those should all be slopes of 0. And negative pi over 2 would be the same, right? Negative pi over 2 would also be 0. And what would pi be? Pi would be
-1.
-1. So we'd sketch these ones. And also at negative pi, they would be -1. That's the same basic point. And 3 pi over 2 would give us what? Back to 0, as with negative 3 pi over 2. And 2 pi and negative 2 pi bring us right back to 1. And you'll note that no matter what the constant I would have attached to the solution to this differential equation, if I were to sketch a curve that went and followed these, the path of these slopes, I'd end up with something that looks just like a sine curve, right? And that's because the solution to dy dx equals cosine x is sine x plus any constant. I could have done it up here, and I'd still have a nice little sine curve. It just would have been with a constant of +3 or something like that. That's the basic idea for it. Nice and easy on ones like this, where we already know what the solution is, and where we already or where we only have an x value within our derivative, so we don't have to worry about the y values. Everything in every column should be exactly the same because there's only x values. Good or no?
Yes.
That's kind of a little trick that we can use to look at what the solution looks like without even solving. So we could do the same thing for something like e to the negative x squared if we wanted to. And if we did that on a small enough scale, we'd really be able to see just what that function that is not explicitly defined as a non-integrable function, we'd be able to see what that non-integrable function looks like. But we're not going to do it with that one. We'll do it with this one. dy dx equals root x squared minus x plus 1. So another one where only our x values matter. And I'm just going to put a few points on here. I'm going to say evaluate this at, assuming each of those is an increment of 1. I put more on the top and the bottom, didn't I? So let's evaluate it at these points. That should be good enough. So when x is 0, what do we get?
1.
Yep. So we're at 1. What about when dy dx is 1?
Also,
Again,
Also 1. What about when x is 2?
root 3.
Yep. So a little bit steeper. And what if we, I'm not going to sketch them all, but what if we put in one that was more than 2, like x equals 3? Goes up even more, right? That's going to become root 7. Maybe I'll put it. So we get even steeper slopes the further to the right we go. And the larger x values we plug in, this x squared starts to dominate the minus x plus 1 quite significantly, and we just get super steep slopes. So this, as x goes towards infinity, our solution to this differential equation is increasing exponentially. Not exponentially necessarily, but very rapidly. Good? What about when x is -1? What does dy dx equal?
Also root 3.
Okay, so as we go this way, oh, didn't mean to do that. These are going to get steeper also. And pretend all those looked nice and the same. And what about when x is -2? What does that come out to be for? Looks like root 7. And so we'll note that it starts off very, very steep, flattens out a little bit, and then gets very, very steep again. So if I wanted to pick the one that went through here, we'd start off real steep, flatten out for a bit, and then get real steep again. Good or no? And this is not an exact science, we just want to get a general shape of what the solution curve looks like. So you plug in a few points and sketch a curve that follows the sort of the trajectories of those little slopes that you've sketched in. And the more little points you put in, the more accurate it's going to look, because the smaller scale you're on, the all the little small fluctuations you'll be able to see. Good or no?
Great.
Wonderful. All right, let's do a couple that have both x and y in them. So we'll do one where we've got them being added or subtracted, and then we'll do one where we have them multiplied or divided. So whenever you have dy dx equals x minus y, or x plus 7y, or 3x minus 8y, or something like that, where it's just kind of these linear little pieces of it on the right-hand side of our differential equation, the best thing that you want to do is to just pick values that you want dy dx to equal. So if I want dy dx to be 0, that tells me that x minus y equals 0, or that y equals x. So that anywhere along the line y equals x, that's the line y equals x, right? The slopes should be 0. So along the line y equals x, all the slopes are 0. Everybody good with that?
Yeah.
Same thing with this. Let's make dy dx equal to 1 now. That will tell me that x minus y equals 1, or that y equals what? X minus 1. True. So anywhere along the line y equals x minus 1, the slope should be 1. And if dy dx is 2, that should be along the line y equals x minus 2. So we'll get a little bit steeper here. Maybe a little too steep. And as we continue down, these are just going to get steeper as we go. And you can pretend that I've done that really nicely at a bunch of points that were indicated, but I didn't. What about the other direction? dy dx equals -1. That would give us y equals what?
X plus 1.
So anywhere along that line, y equals x plus 1, we should have slopes that are -1. And the next one should be -2, so they should just get a little steeper, a little steeper, and a little steeper. And even though my picture is really kind of atrocious there, you can have a pretty good idea of what this function is doing. Suppose I picked this point to go through. Well, it's going to curve out like this, and it's going to curve up like that. Okay. Good or no?
Yeah.
Cool. And these ones like this, dy dx equals x minus y, those are not ones that we will learn how to explicitly solve in this class, but they are things that, like in differential equations class, you'll learn methods to solve them, but not for us to worry about. Okay. Then let's look at something like this, x over 2y. So for this one, we've got a quotient of x and y, and same method here will work for when we have a product of them also. What we generally want to do first is figure out what makes dy dx equal to 0 and what makes dy dx undefined. So what makes dy dx 0?
When x is 0.
If x is 0, y is not 0, right? And what about what makes it undefined? Y is 0, x is not 0, right? Because those would be indeterminate. They were both 0. So if this was the AP test, what they might do is something like this. They put a bunch of points on, like I said before, and say, sketch the slope field at the indicated points. And so we would do that. Anywhere where x was 0, but y was not 0, we'd get 0. And anywhere where y was 0, but x was not 0, we'd get vertical lines. And then we could go in and plot all these other ones, like at 1, 1, what would we get? We'd get a half, right? And at 2, 1, we'd end up with 1. It'd be getting steeper. And as we went out further and further, it'd keep getting steeper and steeper. And as we went up, so to the point 1, 2, we'd end up with a 4, so much flatter. And then this point at 2, 2 would give us a half. So just a little bit. And if we went over here in the negatives, we'd get the exact same thing, except they'd be negative. And we get the same things going down here below. If you plug in 1, -1, you're going to get -1/2, and then you're going to get a -1, and you're going to get a -1/4, and then a -1/2, and so on and so on. Good or no?
Yeah.
And suppose I asked you to sketch the solution curve that went through this point. Well, it looks something like this. And one thing to note when you're sketching these is that you will always sketch a function. Never sketch something that doesn't pass the vertical line test. And you always sketch a function. That's because you're thinking about your intervals of validity. So you want the continuous portion of the function that includes your initial condition. So you sketch the continuous piece that makes it a function through our condition that was given. Our condition here was, let's say, the point 0, 1. And of course, there is a way for us to solve these types of differential equations, what is the name for these types of differential equations? Or it's a quotient of two functions, x and y, or a product of two functions, x and y. Well, we have x over 2y, right? This is a separable differential equation. And I don't know what happened. I thought I had these in the notes right here after this, but apparently I do not. The way we solve a separable differential equation is we separate the variables. So we'll just bring the dx over here, and we'll bring the 2y over here to give us 2y dy equals x dx. We'll integrate both sides to get y squared equals x squared over 2 plus our constant. And let's see, the point we were looking at was the point 0, 1, right? X was 0, y was 1, so 1 squared equals 0 plus c gives us a constant of 1. So we have y squared equals x squared over 2 plus 1, or y equals either the positive or the negative square root of x squared over 2 plus 1. Obviously, we need it to come out to be positive 1, so we choose the positive square root. And if we were to then go in to Desmos, hopefully, we could look at what was it, x squared over 2, right, plus 1. And we would see that, oh, look at that. It looks very similar to what we sketched when we did the slope field, doesn't it?
It does.
It looks amazingly similar to it, which is pretty cool. So we're going to talk more about separable differential equations next time, once I can find where all the notes for it are. I'm not sure where they went. So we'll talk about that. Oof, we got a quiz tomorrow too, huh? Not quite going to get through as much as I was hoping to in the next 2 days. That's all right. We'll talk about separable differential equations. And then we have two more pieces to that, which one of them is another way to approximate the solutions. And another is a specific type of separable differential equation called a logistic differential equation that we'll deal with. I don't know, we may not get to all of that tomorrow, but my hope is that we'll get to some of it tomorrow. And that will be it for today. Easy enough.